then we'll turn it over to you.
Okay, I got something.
Well, good evening, everyone, and welcome to the, this is June 2017 edition of our virtual lecture series here for the Big Bear Valley Astronomical Society. This evening we have Dean Ketelsen with us on the podium, and we've been after Dean for a while to give a talk to our club here. You may recall our last talk was Tom McMahon giving us that nice tour through the Large Binocular Telescope. Several people after the talk started making comments and questions about how they made those giant mirrors and questions about spin casting. So at that point I knew it was time to start twisting Dean's arm to get on our in the queue for our talks here. Dean Ketelsen is one of those people that kind of always seems to have been around. He's one of those astronomer types that's done pretty much everything. Dean has, let's see, I think you were once the 90-inch operator for Steward?
No, I was up at Kitt Peak. I was on the Kitt Peak side.
Oh, you were on the Kitt Peak side. That was before, that would have been even before, was it NOAO at the time even?
Yeah, I was, right, NOAO, I was, you know, Buzz Graves was the fellow I worked with over at Solar. So he was before, we were before you.
Well, Buzz hired me before he left. It was Buzz, Dave Jackshaw, Jeremy Wagner and I. We were the misfits of science over at Solar. So he's been a large telescope operator. I know for decades he ran the Grand Canyon Star Party. He's a very accomplished astrophotographer. Some of you might have even seen some of the famous images he's had of sunset coming down behind behind Kitt Peak. My particular favorites are when it's set behind the McMath telescope, so focus more on those. I believe you are still now doing the nighttime program for the Visitor Center up at Kitt Peak?
No, I retired from that when my wife became ill a couple years ago. Okay,
I thought you went back to doing that for a while.
No, I haven't been back.
Okay. And he's also done a career over at the University of Arizona's Mirror Lab and is one of the experts on the spin casting technology for the giant mirrors up to 8.4 meters. So without further ado, please welcome Dean Ketelsen.
Nice to meet you.
Thank you. After that introduction, I see my time is about up. So are there any questions? Thanks, Claude. Yeah, I only regret I didn't get a chance to work with you guys very much when you were up there. I worked at Kitt Peak for 5 years on most of their telescopes, and after 5 years, I just moved on. There wasn't space to move up, so I went and learned optics at the University of Arizona. So I've been at the University of Arizona since '84. So a good long time.
I didn't get there till '86.
Yeah,
I'm the new kid.
Yeah, but I'm such a fan of Kitt Peak. You know, I go up there. There's a little pullout I use for my own personal observing site, so I go up there whenever I can. It's such a spectacular mountain, as I'm sure you will agree. Okay, you hearing me? Okay.
Absolutely.
All right. Okay, let's talk about the Mirror Lab, where I've been since they opened. I don't do any of the spin casting. I look over their shoulder a lot, and I kind of know what's going on. I can wing a talk about it like I know like I'm talking about, but I'm in charge. Well, I used to be in charge of the polishing crew, and so my expertise was actually in the polishing and testing of the mirrors. And I assume that all of you guys know that the your solar telescope is at the 1.6 meter. That was made at the Mirror Lab.
And we're quite proud of that.
Yeah. That was our first proof of concept for some of the mirrors we're making now. That mirror was sort of hand-figured, which isn't an optimum way of doing it, but it just proved that it could be done, and because of that, we're doing the big GMT mirrors now. Anyway, let's get started. first slide there you see we are nestled under the football stadium. The next slide shows there is indeed a football stadium there, and what you can see sticking out of the top lab is a teepee. That's actually the top of our test tower poking through the Wildcat Club, it's called. The athletic department was looking to build a lounge for their high-dollar boosters for the football stadium. At about the same time that Roger Angel, who you might have heard of, was looking for a high bay area to build a large mirror lab. And the two got together and we decided to join forces. And so over the roof of our mirror lab is the Wildcat Club, which provides great views of football games, but there is actually no entrance between the two, so we can't sneak into football games from the mirror lab, unfortunately. But besides the test tower that sticks out that they have to walk around, on the left-hand side, that large building that adjoins the mirror lab, that's actually our integration lab, where we join the optics and the polishing cells and telescope cells before they leave the building. And we've got offices with the tinted windows and stuff like that. Next slide shows the high bay area. You can see the test tower in the middle of the room, just the bottom part. It sticks up quite a ways through the roof. And the lab, the fabrication lab, is dominated by two large machines. In the far distance is the large optical generator, or log. We're real inventive with names here. That's mostly used for diamond generating, occasionally for polishing when the other machine is occupied. The machine in the foreground is called the large polishing machine, or LPM for short. And it's got two heads, and I'll talk about what we do with that. But you can see it's a nice, large, high bay area. And you'll notice we don't have any cranes that have a large capacity. But we'll talk about how we move the big mirrors around from one end of the lab to the other. The next slide. Back in the old days, when life was simple, this is me standing atop an 8.4 meter mirror. This is our standard mirror size. Why 8.4 meters? Well, people ask us, can you do an 8.5 or 8.6? Well, we could, but we'd have to, we're limited by the crane supports. If the crane supports were just a little bit wider, we can make a bigger mirror, but without enlarging the building, we really can't. Also, when you realize that 8.4 meters is about the most you can drive down a freeway, it takes up 3 lanes the way it is pretty much. And it already provides a pretty good sized target for people that don't want telescopes on high mountains, like Hawaii and Mount Graham and other people that have problems with astronomers. So anyway, that's me. This is, I believe, one of the LBT primaries, large binocular telescope primaries. You can faintly see the hexagonal structure in the substrate, and we'll talk about that too in a little while. Next slide shows a null lens. To be able to test these mirrors, you have to be able to make the aspheric primary mirror look like a sphere to the interferometer. And that's the whole key. To be able to make a mirror, you need to be able to test it precisely. And so on the left is a diagram showing the primary mirror down at the bottom. The LBT mirror is f1.14, so it looks like about an f2 mirror to the center of curvature test of the interferometer. And at the right is the Offner doublet corrector lens, null lens, to make that aspheric mirror look like a sphere to the primary, or to the interferometer, which is up on top. The next slide shows my tool for scale He is 1.96 meters tall, and you can see has a hexapod for positioning of the null lens, X, Y, Z tilts, and all that good stuff you need to park the mirror and move the interferometer where you need it. And at the right-hand side, you see a hologram which provides feedback to us. It's written by a lab in Russia. It's like a zone plate. They write rings on it with the right spacing so that when we park it under the null lens and the interferometer, it replicates the aspheric of the primary and tells us if our null lenses are aligned properly. It's one of the, you might have heard about the Hubble Space Telescope and some of the problems they had. Well, it hit us like a ton of bricks back when we started in 1990 fabricating these mirrors. And one of the ways to make sure that your null lens was working correctly is to have these holograms that tell you when you're aligned properly. Also, we have very much redundancy in our testing that you'll also hear about later. And also the hologram sits at the paraxial focus of the primary, and so we actually run a mechanical tape measure to that surface to measure the radius of curvature of the mirror. We have to, believe it or not, we used to, I don't know, what the heck do we do now? We used to run a mechanical tape measure, and we claimed that it was accurate to a couple tenths of a millimeter with the steel tape, if you can believe that. I'm not sure I do anymore, but this was a few years ago, back in the good old days. The next slide, how do you polish a mirror in a dirty, filthy environment, which the mirror lab is? You know, I wouldn't run around the mirror lab in my stocking feet, and yet we're asked to polish these big mirrors. Some of you might have heard about the 21 men in white that used to polish the Palomar mirror, and when they weren't polishing, they'd be scrubbing things with toothbrushes and keeping the lab clean. Our lab is not particularly clean, but we do scrub the lab and mirror before we start polishing, and it seems to work pretty well. Next slide, we scrub it, scrub the lab, scrub the mirror, and we use filtered air in the lab, and it works pretty well. Polishing back 10 years ago, we used pitch, like people have done for thousands of years, and we use some polyurethane, but we actually still use pitch occasionally. Next slide. How sensitive is an interferometer? It's so sensitive that when my friend Jennifer came to visit me one weekend, I had her lay on the mirror for about a minute, and she got back off. She was in her stocking feet, and the body heat transferred. She's not that hot-blooded, normal human, you know, but you could see where her body heat made the Pyrex expand enough that you could see her position as a high zone on the mirror. So
that explains the Shroud of Turin. Yes.
Good idea. Yes. And it fades over half an hour. Next slide. We have one of our smaller employees, Leslie, standing on top of a mirror in the distance. She makes all of our mirrors look big. She's about 5 foot nothing. So, she's reflected off of, I believe, one of the GMT mirrors. But it's always fun to see labs parked together, or mirrors parked together in the lab. I'm trying to figure out where I am here. Oh, here we go. Next slide. They're jumping to 5 years ago. Now we're on the LSST. Some of you might have heard of that. It's a telescope for imaging the entire sky multiple times. You know, they take 3 pictures of the same spot with some time scale, and they cover the entire sky every couple of days. Has a huge field of view. and they're trying to look for everything that moves or varies in brightness or changes, or they're looking for whatever we can find. We don't know what it's going to find yet. Next slide shows an optical diagram. On the left is the telescope. The primary is 8.4 meters in diameter. Secondary 3.4 meters. And then there's a third mirror built into the primary. So it's actually two mirrors in one. And it results in a very fast, very flat, very large focal plane. You can see the label on that, 3.5 degrees field of view. That's 64 centimeters in diameter, f1.23. It has a triplet corrector, I believe, and filters, but it's pretty much seeing limited. Look at the little squares in the middle there. Those are 0.6 arcsecond squares, and we're effectively seeing limited out to the diameter of the 3.5 degree field of view. So imaging is unparalleled, field of view, flatness, etc. Next slide shows a mock-up of the camera that shows the moon at scale that Suzanne Jacobi is holding. So they are building a mosaic of CCDs that large, 3.3 gigabytes per exposure, 30 terabytes per night, give or take. And oh, by the way, the data is public domain, so you can be the first on your block to look at the exposures as they come down. It was explained to us once, the director of LSST came and talked to our astronomy club, and they have an optical fiber. Somehow the data gets from the Andes, it's going to be in South America, down in Chile. Somehow it gets to Buenos Aires, and it comes up optical fiber up to Louisiana. And I've been told that at the beginning of the night, the data is live, but the data comes through at such a rate that by the end of the night, it's like 6 hours slow. They can't shove the data down the optical fiber fast enough, which I find hard to believe, but that's how they're planning to do it. And this will all be public domain, so you can look at the images as live as is possible, yes? What else was I going to say? I forget. Oh well, next slide. This is a drawing of the profile of the LSST primary. And you'll, if you know anything about the spin casting process, we can't spin two curves on a mirror. We've tried, it doesn't work. We can only spin one curve on the mirror, and so the steep curve for M3 had to be generated out. So we actually cast the mirror so that it was almost, the glass was almost 12 inches thick in the center. You'll see the structure in the primary. Those are the hexagonal honeycomb structure. There's actually large hollows in the glass to make the mirror lightweight. Our mirrors are about 25% the weight of a solid mirror. If you set them down carefully on a body of water, they would actually float. You could put it on the Pacific and put a motorboat behind it and raft it to Chile if you dared. But it would float. So the next slide shows how we generated out the M3 surface, and this is our, we've got a 50 horsepower motor turning a big generator wheel, and you can see you apply lots of coolant to keep the diamonds from melting. We've got a safety roller, that white football shaped roller. It keeps track of where the glass surface is. Our programmer, our paranoid programmer, when we first started programming for this machinery, he was always afraid of the computer losing its mind and not knowing where the glass was, and he was afraid of making ashtrays. That's his polite way of doing it, of saying it. And we didn't want to make ashtrays. We wanted to make precisely controlled mirrors. So there's a safety roller that there's several mechanisms for monitoring that to tell if you're cutting too deeply into the glass. And all those checks will lift the diamonds away from the glass if we're cutting too deep. Next slide shows some of our diamond pellets, how we remove all that glass. The top one is a very coarse diamond, about a 30 mesh diamonds. Diamonds are interesting to machine with, but they will get dull as you use them, and when they get dull, they get pulled out of the metal matrix that holds them. So you'll see several voids in the pellet where diamonds used to be, and then you'll see the little tips of diamonds that are still buried. So as the diamonds get pulled out, the matrix wears away and exposes fresh diamonds.
What is the matrix? It kind of looks coppery or brass.
It's kind of a bronze matrix. It's you can get different hardnesses to wear away more quickly or to act harder, but I don't know the details about that. But it's a bronze sort of matrix that wears away pretty readily as the diamonds get pulled out. The bottom one, of course, is much finer diamonds. I believe they're 100 mesh diamonds, and we use it seldom enough that you can see the pellet isn't even fully broken in across the surface. And more lately, we've been using what are called resin bond diamonds, which is held in a epoxy matrix, which without the metal that you need to wear away with the resin bond, you get much smoother surfaces somehow. I'm not exactly sure why, but we use resin bond before going to loose abrasive or fine grinding on the mirror. Next slide is the start of the M3 surface. You can see we're hogging out glass in the center. And the next slide shows, again, our Vanna White Leslie in the background. 5 weeks of generating, 2 cubic meters of glass were removed, 5 tons, 27 barrels of little glass powder particles. M3 was nearing completion. And once you know it, on the last day of generating, as we were finishing up the inside diameter and the bevels, next slide, 7 years of bad luck, automatically. We broke a mirror. The faceplate is only about an inch thick, 27 millimeters to be exact, and the spindle and diamonds hide behind a ventilation system. I didn't point out in the past pictures, but the glass particle was in the coolant. If you inhale that mist, the glass particles can cause silicosis, so you don't want to breathe the mist at all. So we exhaust it to the roof, and so all this action of the spindle and the diamond wheel happens behind these curtains that you can't see through. And so we were moving the spindle out and not realizing that it would impact the very steep curve of the M3 surface. So we poked a hole in it in 2010. Next slide.
Time to make it a Cassegrain.
No, we did better than that.
Teresa and I were on you toured us through one time and showed us the after the fix.
Yeah. We took away all the loose and fractured glass, and we had, you can see the two holes you see there are actually stop drill holes. There was a live fracture that they had to stop drill to stop the spreading of that fracture. There was a gouge at the 9 o'clock position, and there's another stop drill hole up at the very top of the frame. So there were 3 holes about a centimeter in diameter, and then a about 8 centimeter hole that we had to look at repairing. So we spent the next 6 months. Next slide. We made a practice piece that replicated the hole and looked at ways of repairing it. We developed our procedures and tried them out before we applied it to the mirror. We made a plug. On the right-hand side, you can see the plug that we made that we tried to glue into place. The next slide, for the smaller stop drill holes, we lapped them into place. We used ball bearings to rough in the curvature, and then did final grinding with these glass balls. Next slide shows chopping them off with a brick saw at the right thickness, and we glued them into place. Next slide. Put a cute little bevel on them. Let's see, where am I at? There we go. And try to keep the chips and dimples from being at the front surface. And then the next slide, did the same thing for the large plug. And the next slide shows wicking in the UV curing cement, letting it wick into the bond line before freezing it with a UV lamp. Next slide shows the finished product on the test piece, which effectively looked perfect. And then the next slide shows on the mirror itself, shows the plug in place. With the 2, we enlarged the holes slightly so that we only had 2 small plugs to put in place. So the 2 small plugs and the 1 large one are now glued into place, and it looks perfect as shown in the next slide. This is the finishing stage of polishing. You can see no chips, no dings. You can see underneath the faceplate there's some of the original fracturing left underneath the faceplate, but at the faceplate, at the surface itself, you cannot see it on the interferometry of the final mirror.
That's bloody.
Any questions about that?
What's the diameter of that fix?
Of that repair?
Yeah.
It was about 5 inches, 5.5 inches outside diameter.
Wow.
Oh.
If it was small enough, you could probably just cover it up with something opaque.
Well, that was one of the options, was just to RTV a steel plate there, but I'm always fond of making it look as innocuous as possible. I didn't want to talk about it, but we've since broken another one. Have you heard about this, Claude?
No, this is news to me.
We took a big chunk out of a 6.5 meter. A software engineer was working on a machine. The glass had no right to be parked there, but he was doing some software engineering, and unbeknownst to him, the spindle was moving down slowly. Contacted the beams that support the ventilation system, and instead of wooden beams, we just replaced them recently with aluminum box beams, and it stored up a lot of energy before the bolt sheared, and these box beams came down on the mirror and broke out. My picture isn't wide enough to show you how big it was. It was about 18 inches at the faceplate and about 1.5 meters at the back plate. But actually, we repaired that too.
Really?
But, yeah.
Similar concept? You glued in a replacement piece?
Yeah. Yeah.
Wow.
We didn't repair the back plate. The back plate is still 1.5 meters. It's hard to repair.
Next time I break a mirror, I'm going to call you.
Okay. But The faceplate hopefully won't. The FEA analysis showed, and the modifications we made to the supports, FEA and stuff, said it will be hard to detect.
And I assume there's no problem with thermal expansion, differential. They're the same material, and the glue must have enough elasticity where it does not affect the surface.
Correct. All of that.
Wow.
Well, there are some thermal issues. Because the sidewall and backplate are unrepaired, we've effectively covered it with a carbon fiber panel that is hopefully going to fix some of those thermal issues. But I haven't seen it. In fact, since they're fabricating it now over at Optical Sciences, and we're hoping, I'm hoping to see it someday. But I haven't seen it since the repairs were finished about 10 months ago. Can
you tell us who the customer is?
I probably shouldn't.
Okay. Good enough.
Everyone's happy with it right now, so everyone's happy. I'm just hoping that we don't break any more. Next slide. Back to polishing mirrors. This is still our recent effort with the LSST. We made a new stress lap polisher. We have those vertical, colorful columns. Excuse me. Each of them have a stepper motor, which pushes on a lever, which pull on the stainless steel bands across the top. They exert about 3/4 of a ton of force on those aluminum bands, and because they're working from atop this 2-inch thick aluminum plate, they're actually warping the plate as those bands pull or relax. The stress lap gets bent more or relaxes flatter, and they can change the shape of that aluminum plate a couple of 100 microns, which is all you need for making the spheric of the mirrors that we make. So typically, we'll talk about the shape that we need in a minute. The next slide shows the stress lap on the M1 surface of LSST. Not a lot of stroking going on there because it's such a narrow zone, but hey, it works well. Next slide. We use the laser tracker a lot. You guys have laser trackers there?
We don't, but the original alignment was done from the mirror lab with laser tracker.
Yeah.
And we can't. We've just been really careful with alignment. We can't afford to get you back.
It's a handy tool. We've got like 4 or 5 of them around the lab, and for measuring distances to a micron or so accuracy, they really can't be beat. You can see on the computer screen they're doing scans radial scans along the surface to get a profile of the ground glass. Otherwise, without an thermal infrared interferometer or other techniques, it'd be hard to get a profile of the ground surface without something like a laser tracker. Next slide. Other metrology that needs to do ultrasonic thickness measurements of the glass thickness, so you know how much you're removing. Next slide shows the M3 surface almost polished out. Of course, you can't do them concurrently. You have to do them serially because you can only do the curvatures are so different, and we only have one stress lap. We have to reconfigure it for the other curvature for the other surface. So only one surface at a time can be polished. Next slide shows we can grind. We think, we have a surface that we think is done. We can slap some polyurethane tiles on it, or the brown stuff, and polish with that. And a couple of days of polishing, and we can do an optical test to see if that's what we need to do before we call the polishing or the fine grinding done. You can see some prediction curves in the profile. Profile curve is in red there, and the blue is a conservative prediction of what this stroke is running for 100 hours of removal. So it's we've got some pretty good software for predicting the polishing results. Next slide. Let's get into some figure measurements. This is these are the final figures for the M1, the outer surface, and M3, the inner. Because even these large mirrors are flexible enough that we can fine-tune the shape by bending somewhat. But both of these mirrors are corrected to sub 20 nanometers RMS. And so those are the final shapes after bending the mirror there. Next slide. This is probably beyond the comprehension of a lot of people, myself included sometimes. But when you work to a specification, people, like if you make a 10-inch amateur telescope mirror, you might say, well, it's quarter wave. Well, that doesn't work for large mirrors. You have to meet a structure function, it's called. If you look at 2 points on the mirror, for instance, if you look at a 1 meter, if you look at 2 points a meter apart, if you look at the blue line there, that indicates that it's got to be, what, about 160 nanometers. They can't be more than 160 nanometers in height difference between them. As you go to 0.1 meter separation, you can see they have to be much closer in height. 0.1 meter, 4 inches, they have to be, 34 nanometers within the same height. So as you get to finer frequencies on the mirror has to be very, very smooth. Outside of the mirror at 8 meters, it can be quarter wave-ish, and that's fine, it meets the spec. This is derived from a model of the atmospheric scene and scattering, and there's a bunch of stuff that go into it, not all of which I completely understand. But in fact, the M3 surface has to be a little bit better than the M1 surface. The red line, you can see, because I believe of the curvature is steeper or something, it's a little bit more sensitive to little stricter structure function.
So why does it turn around at the outer limit there?
I'm not sure. I suspect it's because of the models of the scene, what do you call it? The scene cells. At some point, you never see scene cells that are 5 meters or 8 meters in diameter. But I'm not exactly sure.
Okay, so something to do with scene statistics then.
Yeah.
Oh.
Next slide shows what the M1 structure actually was, and you can see, even as soon as you start polishing, you meet the structure at the low spatial frequencies. The hardest ones to meet are that 60 to 90 millimeter, where we just get it under the plot, and we call it done, because it's really hard to get that. I guess that's real. 60 to 90 millimeters is that's where the smoothing is real touchy, because it has to be under 30 nanometers RMS there. Anyway, next slide. That's enough of LST. Let's talk about our current project. This is the Giant Magellan Telescope. A lot of you have heard about that. It uses a center mirror, which is the only on-axis mirror of the system. It has 6 off-axis parabolas around it. And if you look up at the secondary cage, each of them have their very own adaptive optics secondary. And I'm not going to talk about the secondaries. Maybe at the very end I've got a picture. But it has 7 mirrors working in conjunction with each other to emulate a single large mirror. Next slide. I always like this one because so seldom do you see semi-truck used to scale. Interestingly, I believe I heard this from Warren Davison. The mounting that this is riding on is pretty much virtually the same mounting that the LBT sits on. The LBT mounting is robust enough with its only two primaries that it will hold all 7 of these primaries. So I don't believe, I think they ride on the same mounting. Next slide shows our lab again, and there's a GMT1 mirror under the test tower. You can see the yellow lines, the yellow large diameter hoses are our ventilation system. We're drawing air past the backplate to help the mirror reach thermal equilibrium. When we polish the mirror, people think, well, you're polishing it, polishing creates heat, right? And so you've got to cool the mirror off. In fact, the evaporating slurry on the mirror actually cools the mirror a couple of degrees centigrade, depending on the humidity in the lab, anywhere from 2 to 4 degrees centigrade. So we've got to warm the mirror up, actually. But usually we put 3 of these big fan units here and ventilate the cell and the back plate of the mirror, and it reaches some thermal equilibrium in about 8 hours. So we typically ventilate overnight and do our testing in the morning. Also seen here, this is a good picture of the that long black tilted beam there. You see that bar?
Yeah.
It's called a scanning pentaprism. And I think I talk about that. We'll talk about that in a few minutes, but I want to point it out here. That's one of the redundant optical tests that we needed to develop. Next slide shows the state-of-the-art, as we call it. On the left is the LBT mirror, 8.4 meters f1.1. It has about, if you look at the square on the left, it has about 1 millimeter of rotational symmetric asphericity. So it's about 1 millimeter peak to valley on that plot on the left. On the right is one of the GMT segments, the off-axis pieces, has 14 millimeters of aspheric. We don't do anything easy anymore at the mirror lab. It's saddle shaped. There is no axis of symmetry, and because the radius of curvature is 35 meters, it actually doesn't fit in our test tower. But as part of the test system we developed, we got around that. Next slide shows what we do to test. We have a fold sphere up on top. Many of you, if you have a Newtonian telescope and you have a secondary mirror, many of you might have heard that if that secondary mirror has some curvature to it, it will introduce astigmatism. Have you, any of you heard that? If you purposefully put a spherical mirror up there, it will take out what is predominantly astigmatism out of the primary mirror aspheric. So, and then further down on the test tower, where is it? The small fold sphere, there's a 0.76 meter fold sphere. The one on top of the test tower is 4 meters. There's also a smaller fold sphere. And then there's a holographic optical element. And it's the combination of those two spheres plus the holographic optical element that correct the aspheric, that 14 millimeters of aspheric in the primary. Next slide shows maps, 2D maps. The top one is what that aspheric looks like at the mirror surface. 14 millimeters, mostly saddle shaped, mostly pure astigmatism with a little coma thrown in. The middle picture shows after the reflection off the top fold sphere, it's reduced to 6 millimeters peak to valley between the fold spheres. After the second reflection of the fold sphere, you're left with 300 microns of aspheric, and that 300 microns is corrected by the computer-generated hologram to make this mirror look spherical to the interferometer. Does that make sense?
Yeah.
I can see you're all nodding, yes. But yeah, it's a very complicated optical test system. It's not like the old days where we had Offner null lens and anyone could test the mirror. It's a very complicated thing. There's all these optical elements to align. It's extremely tedious and tough.
So you don't have to take it out in the parking lot and star test it.
It would be nice, but no, we can't. We can't.
So,
next slide. It's nicer than to put my picture up on top of the test tower. That's actually my I'm down near the center of curvature of the big fold sphere on top of the mirror. And so you can always impress friends by having them look up while standing at the center of curvature. It's a popular place for selfies. Next slide shows the various ways of testing the mirror. We talked about the principal optical test on the left. In the middle is the scanning pentaprism test. If you imagine one of these mirrors, it's actually a tipped off-axis parabola. So if you I don't really see that black beam in there. But anyway, the black beam of the scanning pentaprism is actually squared to the optical axis. And if you follow the conjunction of those red lines, that would be the focal plane of the telescope. And by shining the beam down, if you see the beam move up in the focal plane, then you have a slope error down the test. And so we can measure low order aberrations by the movement of that reflected beam. And on the right hand side, laser tracker, we use the laser tracker to measure one of these corner cubes as it's moved across the mirror. And so those are our 3 independent measurements. Next slide, there's also something called a Scott's test. It's like a scanning Rocky test that has also saved our butt on GMT1. It's very simple. It's just a TV screen with like Rocky bands on it and a little closed circuit TV. And by careful analysis of the reflected image off the primary, you can back out what the surface figure of the mirror is. Next slide shows some of the results of that. You can see an early principal test of GMT1, and in the middle, the Scott's test of the same surface, and you can see they match very closely. The difference is quite small compared to the amplitude of the figure errors. Okay, next slide. Well, that's the scanning pentaprism test. The arm is perpendicular to the optical axis. So as you can see, those little stages move back and forth. They're moving square to the optical axis. So they get focused up in the focal plane, and any movement corresponds to an error in the shape of the mirror. So they can back out some of the errors that way. Yeah, nothing's easy, but hey, it worked. It took us 7 years to finish the first mirror. So just to get all these ducks in a row is a non-trivial effect to get all these things working. But we recently tested. We made a lot of upgrades to the testing, and we're working on the second mirror now. And we recently brought GMT1 back in to retest it to verify that all of our test methods still work, and they do. Surprisingly enough.
Yay!
Stress Lab wasn't quite enough of a tool to finish GMT1. Next slide. So we developed some other tooling. Next slide is an orbital polisher that we used. I liken it to carpentry work. It uses a dwell control. It's like if you have a high spot on a cabinet you're making, you sand more on the high spot and stay off the low spots, and the figure will improve that way. And it works very well, very good convergence on using the dwell-based tooling. By the way, the mirror, again, the mirrors are so aspheric, 14 millimeters of A-sphere. The lap is called an RC lap. RC lap is labeled on the right-hand side. RC stands for rigid conformal, which is sort of an oxymoron term if I've ever heard one. How can it be rigid yet conform to the surface? Well, it turns out that I woke up Siri on my phone. The RC lap is made out of silly putty. It's a silly putty lap behind a rubber membrane with this polyurethane tooling, a polishing pad underneath it. And silly putty,
Literally?
you can literally. Did you know you can get silly putty in 5-gallon buckets?
I didn't know you could still get silly putty.
Yeah.
Anywhere.
We've got like 4 gallons left. But anyway, if you can hit it with a hammer and it barely dents it, and yet you can push on it steadily with your thumb, and it does what it needs to do. As you're rubbing over a high spot, it will resist immediately bending over that high spot. It retains the shape enough to hit a high spot, and yet it will slowly, as you march around the mirror to the different parts of the mirror, it conforms to the change of aspheric. So anyway, well, next slide. Sort of reviewing some of our predictions and the results, what predicted and what we actually got matches pretty well. And our 24-hour facility now, we actually do a 27-hour run nonstop. So all this, we don't quite have the full coverage on weekends. We don't have Saturday and Sunday nights covered, but otherwise we're 24/5, and then some coverage on weekends. Next slide shows, oh yes, we actually do walk-on mirrors that are finished. You can use stocking feet, or you have shoes that are not worn anywhere else. So, and placing fiducials to map out there's enough distortion in the imaging of some of the testing that you have to do a map of the distortion every time. So every measurement requires placing fiducials to map out where you are, where the errors are. Next slide shows what the mirror looks like during a test, and so those fiducials are recorded concurrently so that you can see how it morphs to the real mirror. Next slide is a demonstration of how aspheric these mirrors are. You know, some of you have probably, if you have a test plate under monochromatic light, if you have 2 spheres, you get straight parallel fringes that match each other, or 2 flats. This is a picture of fringes from a test plate that matches the GMT mirror, and you'll see it's got like 40 or 50 fringes of astigmatism there. That's on an 8-inch test plate. That's how much aspheric across an 8-inch mirror. And we actually tried to use this to our interferometer. The slope errors were high enough at the edge that our interferometer, 35 meters away, couldn't track the errors well enough. So we actually tried to use this test plate to measure the profile of the mirror. You can see that down at the lower right, how it goes up and down by a few tens of nanometers. But yeah, it's fun stuff. Next slide shows we can play some tricks, especially with GMT, because the 6 mirrors are a little bit independent, because you can You can shift them laterally, I think up to 2 millimeters, and you can also rotate them. So at left, upper left, is how the mirror was measured. This is the measurement of the mirror at upper left. At right, if you rotate and translate slightly, you can improve the figure a little bit. At lower left, that's what you're left after rotating and translating. And that you can bend out by applying very minor forces over the 160 actuators that support the mirror. You can bend out astigmatism very easily, which is what that mostly is. So you can bend that out with a few pounds of force, and that lower right, that's the resultant RMS. This is before it was finished. This is, I think it says 26 nanometers RMS, and RMS forces were 16 newtons. I'm not sure how many pounds that is. Not very much. Next slide shows the finished figure of that mirror. 19 nanometers. We try to get under 20. And you can see there's probably places where we could have improved it some more, but if it meets spec, hey, done. Next slide shows the images. That's a lower, well, you'll always have scenes, so you never get the upper square. The lower square with 0.2 arcsecond scene, that's a 2 arcsecond square box there. But it'll work well. Next slide. This is the first picture. First time we've had the first 3 mirrors in a row. At lower right is GMT1, which has a blue coat protective layer. The middle is GMT2, and the back is GMT3. So all of those are various stages of completion. GMT1 lower right's finished. GMT2, we're starting to work on that right now. GMT3 in the background, we're about to start generating the front surface. So, but those are the first time that those 3 mirrors were apart next to each other. We've been modifying, next slide shows, we've been modifying some of our tooling. We've got a new orbital polisher at upper left, and we've changed the stress lap so that it's no longer strictly a rotation and radial movement. It does orbital motion too, like the small orbital polisher. We now have a stress lap orbital. Next slide shows we've been trying to get away from loose abrasive lapping, and we're going to bound abrasives. These pellets, these little hexagonal pellets, have embedded diamonds in them, and we're trying to use the bound abrasives because we think it's dangerous or safer than loose abrasive lapping. Back in the old days when we had rigid tile and your delicate glass separated by 12 micron loose abrasive particles, when you have big laps and chances for accidents, if those were to ever grind together, you get massive amounts of damage. So we're thinking that the bound abrasives might perform better. Next slide. Do you have an arrow that shows up? Can you play that video?
There we go.
This is a little,
Wow.
This is our old, it's a time lapse, so there's some stroboscopic effect on some of these. But this is our Mark 1 orbital polisher. And the thing to notice is that it speeds up and slows down. When it comes to a high spot that's defined in the map, it will slow down and spend more time rubbing on it. And when you get to a low spot, the map or the mirror will speed up. And every rotation, it moves another centimeter inward or outward. I forget offhand about this particular stroke.
Can you guess what speed up factor there is there? What's the real time look like?
I think it's something like 15 to 1. It's a pretty huge amount. This is a view from across the mirror, from under the stress lap. You see the stress lap on top of the mirror. or on the top of the view.
What was that man doing?
And again, you got a weird but
there was a question about what was that guy doing with the hose?
he was washing the stuff towards the center. This is the end of the run now, so we're cleaning off the mirror. Note the clock. If you can see it in the background, I can't see it at this resolution, but it's like 20 minutes after. One of the problems with the GMT mirrors, they only give us a 2-inch center hole. It is very difficult to wash a mirror this big and get everything to run down a 2-inch hole in the center. I assume it's like Coriolis force. It runs down and then misses the hole. And
you can really see the symmetry of the mirror as it rotates there. Different story. Oh my goodness.
Yeah, I was going to point that out. I don't see it in your view, but yeah, if you look at the reflection, that distortion is actually that 14 millimeter saddle-shaped A-sphere in the reflection. There's another view that you'll get it even a little better in a minute. So yeah, they're rinsing and scrubbing and squeegeeing. We use a squeegee to dry off the mirror as quickly as possible. Because again, you don't want the water to evaporate off of it, because that'll only cool the mirror down more than you already have. You see the clock in the background? How much time has gone by? Probably like half hour.
It's coming up on 4 o'clock. You were about a little over half an hour.
Yeah. And you see, we're not wasting our time either. So it's like, yeah. And then Leslie goes out and dries off the last of the wet spots. And then we have to de-skirt it. We take the skirt off the outside edge, so that there's no weight hanging off the mirror before we do an optical test.
Cool.
And here's the reflection to show that 14 millimeters of A-sphere.
That's beautiful.
Pretty cool, huh?
Yeah.
And here the air cart lifts the cell off the turntable, and then we use compressed air to run the air cart, and that pulls the mirror out under the test tower, and then we lower it down on the supports there, and we're ready for test.
Wow.
So yeah, the biggest cranes in the polishing lab are only 5-ton capacity. So the cell plus the mirror is something close to 40 tons. So no way that the cranes would be able to help us much. Let's see here. Okay, next slide. I think that we'll skip that video. We'll skip that video because it's superfluous. The casting, we've learned a lot over the decades, especially for polishing, but the casting process is pretty much unchanged. Next slide shows the casting lab dominated by the rotating oven in the far distance, and the handling ring on the left, and a space for storing large volumes of glass and refractors. Next slide. This was taken about 2 months ago. This shows our casting supervisor, Randy Lutz. They're just putting the tub walls on. Tub walls are what hold the mirror together when it's spinning to hold the bulk glass in. Next slide shows the hard refractories. These are the only parts that are recycled from mirror to mirror. The base of the mirror on the upper right, base of the mirror has holes with nuts down below, and the screws hold the soft refractory cores down to the base through these holes in the hard refractories. show the Inconel bands wrapping around. And by the way, these pictures that you're seeing here, every slide here is taken like 2 days later. I mean, these guys have been through this so many times, work so well as like the six-person crew that they can build this thing, you know, up from scratch in a very short order. But these are the Inconel bands that terminate, that hold the tub walls together. Next slide shows the cylinders that hold tension on the Inconel bands. From room temperature to 1200 degrees centigrade, which is the highest temperature we reach, the bands change in length by 10 inches. So the cylinder has to have a draw of 5 inches to be able to keep a constant pressure on the Inconel band. So that's why the cylinders terminate the bands, because they grow and contract with temperature. Next slide. This was about 2 months ago, and they were going to do a band seat firing. They're lowering the top of the oven down over the hard refractories and the Inconel bands, so that they do their expansion and contraction and get the hysteresis out of their position before they start building up the mold. Next slide. This is the current picture as of Tuesday. This is Damon. He was working by himself. He's gluing the tops on the cores here. If you look at the row of cores on the bottom, you can see there's about a 1 centimeter gap between the individual cores. That's to provide the glass to run down and make up the structure of the honeycomb mirrors. You can cover the cores as long as they're not at the edge. The edge cores, as you build the mold out further, each of those is cross-pinned to the adjacent cores, so the outer row of cores can't be covered. He's working on the second row of cores in. Next slide shows them. They have a CNC machine that machines out the cores. There's 1,600 and some cores in a GMT primary, and because of symmetry, there's at least 6-fold symmetry, some 12, probably some 18 and 24 as well. But there's like 160 different cores that have to be programmed into the machine, and it's kind of fun to watch the machine do that. Next slide. It goes, you know, I guess I'm easily entertained watching a CNC machine do its job, but it takes about 8 or 10 minutes to make one, and it's kind of fun to watch. It's kind of cool. They test all of them for strength. They have a vacuum fixture, and they sometimes fail, and they have to make a new one. But these are some of the unusual shaped ones near the edge. You can see it's not a true hexagon shape on this one, on the speed machine on the left. Next slide. This is all done in a enclosed chamber with dust collection, because again the ceramic refractories are very dangerous for your lungs. GMT5 casting is currently scheduled for this fall sometime. Next slide. This shows a different mirror as they're approaching the edge. All the cores are fastened to the hearth plate. You saw the hard refractories before, and there's those long bolts are screwed down the bottom to hold the cores down. And at right, they're doing the last couple dozen cores there to finish one of the previous molds. Next slide. After that comes glass loading. 20 plus ton. Oh, there's actually a pre-fire before they do this. They again heat up the mold to 1200 degrees and back again, and then they do a complete inspection and cleaning of the mold before they do the glass loading. But they load 20 tons of glass. This is E6 glass from Ohara in Japan.
The preheating, that's just to test and maybe to outgas stuff, or what?
It's to test the outgas. It's for some of the things they expand and they contract, and they've got some hysteresis, so they don't come back to the same position. So you don't want that to happen during a mirror casting. You want it to expand, contract uniformly. Yeah, Ohara makes it about a ton at a time, very uniform quality. And once they have these 1-ton pots and stuff, they cleave it so that it melts together for us. It melts together without trapping any air bubbles. Next slide. This is when we do the casting. Casting day, you have typically open house for VIPs to come by and feel the heat. You can literally feel the heat radiating off the thing. At the left is Richard Karras, who the lab was recently named for. If you give us $20 million, we'll name something after you two. But he was an early supporter of us. All of the load cell mechanisms that we use in our telescope cells and throughout the lab are from his company, and he gave $20 million, and so we named the lab after him. And he recently died about 6 months ago, about a year and a half after the renaming. So kind of cool. Next slide. Reveal day. This is the GMT4 mirror, the only one with the center hole. And it looks. They all look beautiful. They have a fire polished surface. If you see the upper left picture, you can see the reflection of the inner tub walls reflected off of it. They have that flame polished appearance. Next slide. We need to glue on the spider to it, and silicone bathtub caulk is what holds the mirror to the spider. Silicone bathtub caulk will lift the 30 tons of glass plus cold mold out of the oven and hold it upright for mold removal, and then it'll also hold it backside up while we fabricate the back plate of the mirror before we finally wire saw off the silicone RGB to put it in the polishing cell. So we lift it out of the oven. Next slide shows it uses high pressure water to wash out the interior mold. So the mold, of course, is only used once, and then we're left with a hollow mirror that would float in water because it's only about 25% weight of the solid mirror would be. Okay, a couple of pictures. Next slide shows this is one of the adaptive optic secondaries for the LBT. It's a little bit dated because it's a few years old, but the mirror at the bottom has about 660 little magnets glued to secondary, which is about 1.6 millimeters thick. If you can imagine a 1.6 millimeter thick secondary mirror that is accurately figured, by the way. Those magnets will go up into the reaction body up on top and react to voice coils that will then bend the mirror minute amounts to correct the scene in the atmosphere. Next slide shows the Gregorian secondary from the telescope side. So yeah, it's a Gregorian secondary, so it's up beyond the focal plane of the LBT primaries. But the results are quite spectacular. Next slide shows some of the early pictures that I've seen at left without the compensation and at right with the compensation. You can resolve well under a couple of tenths of an arc second. Along those same lines, since that instrument was developed, one of the things that I like to do personally, since it's sort of my baby, I feel that LBT is kind of mine. Next slide shows one of the instruments that I like to track. It's called Argos, which is the Advanced Relay Ground something or other. You might know, Teresa.
I'm trying to remember. Ground.
It's actually
Optical sensor? Optical.
It's not that simple. There's a couple other words in there. But anyway, each mirror has its own constellation of 3 lasers that surround the beam, and it allows you to improve the scene over a very large 4-arc field. And star images improve by a factor of 2 or 3, which doesn't sound like a lot, but if you improve the star diameter by a factor of 3, that's about a factor of 10 in intensity. So if you make a star image 3 times smaller, it gets 9 times brighter. So it's an impressive instrument from that respect. This is a picture that I took from Safford over their March observing run. And I don't know if any of those trees are still there anymore since they've had the fires recently. But anyway, that's that. Next slide.
Hey. Hey, dude.
So I have a blog. My wife started the blog, but I write it now. It's the ketelsen.blogspot.com, and a lot of this stuff is on it. I like to write about work and show off a little bit, and I do a lot of other astronomical stuff. You got time for a couple of short pictures and videos, or?
Well, sure.
Argos video.
Well, let me take this down and queue up for that. Where did that go?
Claude, at some other time, could you spend a couple minutes talking about how a green laser enhances the view?
Maybe.
At some other time.
Okay. Which video are you looking for?
Do the 7 March LBT Argos.
Up to the other end. Up, there you go.
This is a picture taken every 30 seconds. Yeah. I was parked down in Stafford and I took a picture every 30 seconds. And it was from, it caught the dome opening, first object of the night, second object, third object. And they turn around, other one way, and they turn the Argos on. And you can see there, I can see enhancements. There was a controlled burn, I think, over at Sweetwater Water Treatment Plant. And you can see there's a layer of smoke right over the telescope dome. You can see a little bit of an enhancement of the reflectivity in there. But this is about 3 hours worth of just exposures every 30 seconds showing the Argos laser. And they have spotters that look for airplanes, and they can kill the beam if they need to, if an airplane strays too close. So that's kind of cool. I like doing stuff like that. Well, that's that one. And I don't know if you guys are interested in my little adventures, but there's a picture, 19 March, Venus.
How do I get that?
Escape.
Escape is,
Not escaping?
So I didn't have
21
the whole
March
screen.
Venus.
19 March. 19 March 1st. This is not a poor picture of the moon setting behind Kitt Peak. This is actually a picture of Venus during its inferior conjunction a couple months ago. And the problem is that, you know, I try to do these little landscape things, and the sky was still too dark, and Venus is heavily overexposed, but I couldn't expose any less than I wouldn't get the telescope domes. So then go to the next image. There you go. This one was taken 2 days later. It was still was in a brighter sky. It was with a longer focal length telescope, so you can see the seeing effects in the lightning rods, but it was nice to be able to see the crescent Venus, even if it was highly distorted in the picture there. Do you see Venus? I don't see Venus in that picture.
Yeah, it's
up in the corner.
yeah,
Is that the McMath Pierce?
yeah,
There it is.
yeah. That's the McMath Pierce, and the tower to the left. That's where the old vacuum tower was, and later was replaced by the Solus instrument that is supposedly coming here, maybe later in the year.
Cool. You can show the last one. That just shows Venus sitting behind the water tank up at the telescope, the mountain profile. And I've gone through and identified all of the everything but the trees, pretty much. Anyway, that's really about it. I don't think we need to see anything else.
That's spectacular, I think.
I try to have fun. Come visit my blog, and you'll find more crap there.
That's a technical term.
Well, let's first of all thank
Yes.
Dean very much. Thank you, Dean. That's very much appreciated. Do we have any questions?
Wow. Right.
How long is it anticipated until all of the mirrors for GMT are finished? Oh, I had to ask that one, huh?
Well, let's see. 7 years for the first one times 7 mirrors plus a spare. That's like 8 mirrors times 7 is 56 years. Now, supposedly they're going to come along faster and faster. We're hoping to do this one in 3 years. So I'm not sure, but hopefully once we get everything working, we'll get it down to a science and less of an art.
So are they going to do first light with fewer than all the mirrors in?
Yes, I believe the first light is with 3 or 4 mirrors.
I think I've heard that.
Where are you going to store some of these other mirrors? You're going to be running out of space here soon, I assume.
Yes, we have storage space down at the airport, so there's a facility down there to store them once they're finished. I suspect they might actually go to Chile as well. The first mirror, interestingly, even though the first mirror is finished, it may well be the last mirror to leave, because it'll be like the standard ruler to measure all the other mirrors. That makes sense?
Yep.
You want all the other ones to be just like the first one. So that may actually be the last one delivered.
And who's doing the adaptive secondaries? Is that our...
I have not heard. Similarly, I have not heard who is doing the secondary for the LSST telescope. I don't know that either.
If you're going to,
I don't get out much.
if you're going to store the mirrors in Tucson, is that in a controlled environment? Do you have to worry about temperature?
Tucson's definitely not a controlled environment.
It was only 109 today, though.
Yeah, right.
Oh, you're talking
Compared to 116 yesterday, I almost felt like going for a jog. I would hope that it's air conditioned. Most of it, we have a lot of storage facility at Ralph's Transfer and Storage. I don't think they can handle our 8-meter mirrors. I believe there's hangar space down at TIA where this is stored, but I'm not sure of the details. Once the mirror leaves the building, I don't keep track of it.
And just one note, when we saw the big finished mirror circling around, it was just amazing to see the asymmetry in the reflection of the mirror as it went around. I would have guessed and lost a keg of beer that it would have been flat or something not asymmetrical.
No, well, it has the 36-meter radius of curvature. But yeah, if you put a mechanical indicator on that, it will go up and down 14 millimeters.
Good golly.
Before you go, can you say a couple words about the Grand Canyon?
It's going on right now through Saturday. I was there Saturday and Sunday, and Monday I clouded up, and I had to be in town for other stuff. But the Grand Canyon Star Party, this is the 27th year. I started it in 1991, my wife and I got married in Vegas. We kind of ran off and got married. And we happened to be traveling with a pair of 20 by 120 Japanese battleship binoculars. And we set them up at the rim, and we were like looking at hikers and river rafters and having a good time seeing what we can see with the 20 power binoculars. And we turned around, there were 20 people in line wanting to look through the binoculars with us. And so I sort of got the idea, you know, we should bring some friends next year for our anniversary and have a star party. And in 1991, I was able to talk 3 people into joining us. And we had Daryl Nye, David Lamine, I believe Mike Terenzoni came with us that first year. And since then, currently the first night this year, they had 50 telescopes. Over the course of the week, there's typically 100 astronomers that come, and we get about 2,000 public a night, 2,000 visitors a night from the Grand Canyon. The park, initially the park sort of gave us a special use permit. Yeah, you can come, just don't make any noise, or, you know, keep it down, keep it down. And now it's like the big things that they promote. Dark Skies National Park is all of a sudden a big business, and I would like to think that I had some small big that. So,
Definitely.
but it is so fun. You know, when people are on vacation, especially at the Grand Canyon, I don't know if this is the same everywhere, but people are so happy to look at whatever you want to show them, whether it's the crescent moon through a 3-inch telescope, or Dennis Young had his 28-inch there. I've got my C14. I was running Saturn at 400 power, just perfect scene the other night, and, you know, people were crying. It was just amazing. Wow. You know, it's nice. It's nice that the view is good, but the sky is so dark there that anyone can be impressed, even the astronomers. So, anyway, and this is
That's great. Ask me about the stars.
This is a T-shirt design this year. Ask me about the stars.
Nice. Well, we missed you at RTMC this year, and can we attract you out next year? It's the 50th anniversary coming up.
Ooh, sounds like a good event.
Yep.
My friend Mike Spooner, I talked to him at the Grand Canyon. He's going to bring a 36-inch telescope.
Nice. Okay, is there any other questions, or should we let Dean get back to his evening?
Yeah.
Well, please thank him once again.
Thanks, guys. I'm glad you enjoyed it.
And of course, you're welcome up here anytime. Hey.
Okay.
It was only 85 today, by the way.
Oh.
And Fahrenheit.
All right.
Goodbye.
See you guys.
Okay, good night.